Okay, let's begin. So, first of all, are Josh and Zach right? They tag team the warm-up. Do you like what they did? Check their work on those. I tried to make it like throw interesting things at you, like everything I could possibly think of: fractional exponents, negative exponents. Trying to catch you, and trying to. Oh, the derivative of 15 to the 6th. That's 6 times 15 to the 5th. Oh wait, no. Right, it's just a constant. Keep in mind what the variable that we're taking the derivative with respect to is, and all that. Make sure you understand what we were asking for here. Of course, we're asking for the second derivative. So I haven't checked piecemeal every single thing yet, but yeah, you guys have maybe. You like them? I'm gonna make this go away in a second. So if you want to criticize something, then do it quickly. Quick before Albert gets a. Oh, sorry, Albert.
It's okay. I'm almost
Get it? Okay. We want to still be in 3.3 today in rules for differentiation. And today we want to focus on one piece of this section called the product and quotient rules. Let me ask before I even begin too, just kind of, I don't think I need to talk too much about the homework, but it's going well. Are you enjoying using the power rule? Do you feel powerful? It definitely quickens your work. I do still have that challenge out there to prove some of the fact that it works for all reals. We provided a good, some good observational proof that it seems to work, but we'd like to actually maybe someday prove those. I don't know. Kira came through for me. She proved it for any positive integer n. So using the binomial theorem. That was cool. Strong work. Okay. But what about 1 over n for integer n? What about, right? Build up the cases here until we get to all reals. And irrationals is maybe without, the irrational powers is outside of your ability to, well, I don't know, I shouldn't say that. Nothing is outside of your ability. But it might be the subject of a real analysis class in college if you were to go there. So, but I think you get most of it. All right, so we have 2 rules to add to the mix today that are going to help you. And again, we're going to try as much as possible in this course to never provide anything without justification. So we'll prove this in a second. But there it is. This is how you take the derivative of 2 functions, the product of 2 functions. And we'll say why that works in a second. Said out loud, you might say, oh wait, I don't think I have it here. The first times the derivative of the second plus the second times the derivative of the first, if we're multiplying 2 functions together. And the note there is, of course, critical. Some of you might have even been tempted in the homework last night to take the derivative of a product of 2 functions by taking the 2 derivatives separately, and then be like, oh, well, it must be just the product of those 2. Well, there are a number of ways to dissuade you of that. One is to actually check and see that it works. One would be to graph the 2 results on your calculator and see what the difference looks like. I don't know, a couple different ways. I think it would be very easy to check pretty quickly that, if you try to do that, you're just wrong. You really do need to do this more complicated thing, even though you might not like it. Is it clear what we're asking here? If not, it will be in a second. There are 2 ways to do this one. Did you have one like this in the homework last night, by the way, at all? Okay. And last night, this weekend. Oh, did you already? Oh, because you're. Oh. Well, the point I'm making here is that you could have done this one prior to now by just multiplying it out. So I'm suggesting that you multiply it out and take the derivative using technology that you already understand, just the power rule and the linear property. And then also try this new rule as well, the product rule. See if it'll work to do the first function, or I guess if it's not obvious, we're considering this first function in parentheses to be f, say, and the second one to be g, say. Okay? So try it both ways, and just please verify that you do get the same result both ways. Go ahead and take a minute to do that if you've never. I assume that you know how to multiply it out and take the derivative. So at least do that. If you need some help with the product rule, that would be understandable, because we've never done it before. Did it work? Huh? still not be the whole story, because then you get 1, not negative 1. But anyway, there's some work to do. Is anyone unclear what I just asked? I think helps clarify the task. You guys understand what I asked? I'll do the product rule with you here, and you can do it the old way, and we'll see. You can tell me if we get the same answer. Okay. So y prime is equal to the first thing times the derivative of the second thing, which is what, 6x squared plus 5. So far, so good. So if this is, say we call this f and this g, this is in fact what we have up there, right? Isn't this f g prime plus g, the second thing, 2x cubed plus 5x, f prime, which is what? All right, does that look good? And actually, we're done. I mean, for all, like, for most intents and purposes, that would maybe be good enough. Like, we could just stop there. There it is. But just to prove the point that this is, in fact, the same thing as you got if you multiplied those together first and then took the derivative. We might just multiply this out to see what we get. This is not fun, but we'll do it. Okay. But just do keep in mind that we already do have the derivative. Like, if someone asks for the value of the derivative function, that is, what's the tangent to this curve? What's the slope of the tangent to this curve at, like, you know, x equals 2 or something? I could plug it in here. That'd be okay. You know, but all right. So 6x to the 4th plus, what do we get? 18 and 5 is 23, and 10 is 33. Is that what I just said? Yeah. X squared. And there's a 15 in there. And there's also another x to the 4th. I should have added that earlier. 2x cubed, and I should have added that earlier. Shoot. I thought I could do it in one step. All right, check my work on this. Is that what you're getting?
Yeah.
Again, either way, you should have been getting that answer, whether you did the product rule or whether you did it multiplied it out first. Yes? Not a proof, but at least it seems like it's working. Here is a proof, though, if you'd like it. Is there any questions on how to use it? That's. I don't have much to say. I mean, I think it's pretty straightforward how to use it, right? You just like do what the rule says because the rule says it. First times the derivative of the second plus the second times the derivative of the first. All right, can I present one proof to you? And then I have two proofs for you, just for fun, okay, of this rule. One that's kind of quick and dirty using the definition of the derivative, and the other one uses the definition too, but it appeals more to your intuition. This one I think you'll like. The algebra will be all correct, but you might not have a lot of intuition why I'm doing what I'm doing. All right, so again, and by the way, these two proofs you don't necessarily have to copy down. You can find them online too and things like that, things like this, or you can watch the video. So just sit back and like enjoy as we like think about these proofs, okay? So do you agree that I've done nothing to change this? But by the way, isn't this what we desire, the first line? This is the product, fg. So that we're plugging in x plus h and x, right? Okay, all right, just to be clear. And now I'm introducing this crazy thing in the numerator, which is just 0. So we're okay. Maybe you kind of can see where we're going with it. I'm going to factor out, now I've made the red go away here. I'm going to factor out a g of x plus h. Do you see this guy, g of x plus h? Out of the two things at the beginning that have that. Do you agree that I haven't changed this numerator yet? And I do the same thing over here with f of x. I pull that out. Stare at it until you see it. Bavesh, don't laugh. Look. You'll get it. All I did was factor something out. Yeah? You see it? Okay. And then, guys, I'm going to just ask to take all these limits separately, which is completely fair, right? That's a property of limits that we have available to us. The reason you can see now, maybe all the way back to here, why I did what I did. Do you see what this is over h? I mean, already you can kind of see where I'm going to go with this. This is times this. I put limits of h go to 0 everywhere in different places. Plus, this is the f of x, and this is this piece here. Yeah? All right, and then the result follows. If this is, what's this here? This is also known as f prime of x. This is down here, g prime. What's this? This is just g of x, isn't it? So there it is. So there's one proof. Stephen, you liked it. Yeah, okay. All right, so that's one proof of the product rule. Let me give you one more that I think you're going to like, okay? I want you to also think about what you're doing when you multiply two functions. You can kind of think about these as like the length and width of a rectangle that's changing. And we're asking, what's the question we're asking when we ask about the change in the product of two functions? Well, in this context, you're asking about, hey, if I change this function by a little bit and this function by a little bit, how does the product, how does their area of the rectangle, it used to be this, how does it change when I change the two side lengths? Is really kind of the question that the product rule is kind of asking, isn't it? So do you like this language? I'm going to call two functions now instead of f and g, L and W, just for fun, because that kind of evokes in our mind length and width. So that's cool, right? So we're wondering, what's delta A? If you change the length by a little bit and change the width by a little bit, what would the change in the area, delta A, be? I think you'd agree that if we change the side length L by an amount delta L, then the new side length is L plus delta L, and likewise for W. So the new area, which it used to be A, the new area is A plus some amount of extra area, yeah? And isn't the new area this times this, then? Yeah? And I know how to use the distributive law really well. I just multiplied this out. FOIL, if you will, okay? Here's the picture. Here's the original area in white. And then I'm increasing the length and width by an amount. And I've labeled these in color, coordinated them to the things up in the equation, okay? So you can see. Isn't this area, this red area, isn't this L times delta W, for example? Isn't that how you calculate the area of a rectangle? All of them are shown nicely in this picture, okay? So the area of the whole thing is the old area plus, so what's delta A in this picture? Well, delta A is like the area of the three colored regions, isn't it? Okay. You staying with me? Again, you don't have to copy this down. I just think it's nice to see the visual. Because the other one, the first proof is very algebraic, but there's not very much intuition. Like, why would you just introduce that random term? All right. Now, keep in mind, let me go back to that previous equation for a second. Right here. Do you see there's an A here on this side of the equation? And there's also an LW on this side of the equation. Well, those are the same thing, aren't they? The original area is LW. That's what it is. So if I subtract both off each side, then I'm going to have an expression for delta A, the change in the area. It's going to be the colored things. Okay? So there it is. So the change in area is this. Is it already starting to look familiar? Maybe? Dividing through by delta x gives this. I just divided by delta x. It's a thing. I can divide by it, okay? As long as it's not 0, which it's not going to be 0, okay? Because we're going to assume that it's an infinitesimally small thing. Okay, eventually we're going to take a limit. So if I divide by delta x everywhere, I get this, I get this, I get this, and I get sneaky move, but that is me dividing by delta x. Do you agree? I mean, I divided by it twice and multiplied once. So is that tricky? It is me dividing by delta x everywhere. Okay. All right, and then all we have to do now is take the limit as x goes to 0, and we get the desired result, right? Over here, this goes to 0, why? Well, because we're multiplying by something that's getting close to 0, right? So this is the product rule in terms of L's and W's now. You could think about it as a rule governing the change of area, given that two side lengths are changing, right? Yeah, Albert. So you might think about it like if we're talking about the length and width or something, you're changing them. Maybe it's time, right? Or maybe I should use delta t or something. Some independent variable that both the length and width are relying on as we change, right? Could be anything. It doesn't really matter. In fact, the product rule, I mean, you wouldn't even have to have the dx's in there for you to express it the way it is. The independent variable is not really the important thing here, actually. All right, let's say something about the quotient rule. I'll give it to you first, and then I'm actually going to ask you to prove this one just for fun in a minute here, so we'll give it a try. It's a little bit hard to see in Leibniz notation. You might just, not write it down. You can just write this one down. Here it is, f over g prime. So bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom function squared is how this goes. And this is something that you'll want to, that you'll want to commit to memory. The quotient rule is something you'll need to know. Okay, so we have a memory device to help you learn it. Okay. We are gonna chant it together in a minute here. All right, there used to be, in order to appreciate what this says, you have to know there used to be actually crackers. I don't know if they still make them or not, but called high-low crackers. Okay. All right. So the reason this is on yellow paper and all pretty and everything is so that you can cherish this forever. Okay. It's not just like another handout. This is the quotient rule. Okay. So if someone were to ask you, so like I said, so there's this old cracker brand. I don't know. Like I said, I don't know if they still make it, but Hi-Ho. All right. So I'm stealing the Hi-Ho box of crackers to do this. So someone might come along and ask you, hey, what's the derivative of high over ho? Right? Someone might ask you that, right? You've probably been asked that before, right? Okay. Well, the answer is, if we use this is a quotient. If we use the quotient rule, it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function. Do you understand by d, I mean the derivative of that thing, all over the bottom function, not the derivative of the bottom function. Just over the bottom function squared. Okay? So the way this sounds out loud that makes this very easy to remember is ho d high minus high d ho over ho ho, right? So that's how it sounds, right? And it's very easy to remember because no one would ask you for what's the derivative of ho over high. That doesn't make sense, right? Well, because high is up high, right? Come on. Stay with me. And ho is down low. Okay. So, all right. So, and the other thing that might be hard to remember as you read this out loud and memorize it to yourself is why would ho be at the end? Why isn't it high d ho minus ho d high? Right? That'll be confusing. Right? You with me? That's gonna be hard. But when you say high d ho to someone, you're saying goodbye, aren't you? That's the end of the fraction, right? Hi ho. Don't you say that to your friends? Right? Okay. So there's no way you could ho d high at the end. That wouldn't make sense, okay? No one even says that, okay? So I'll say it one more time, me, and then we'll all say it together in a second, okay? Okay. So someone might ask me, Mr. Chase, what's the derivative of high over ho? And I would say ho d high minus high d ho over ho ho. Okay? So I'm going to ask you, class, what's the derivative? Are you ready? You have to be ready. Albert, are you ready?
Albert, are you ready?
Okay. Class, what's the derivative of high over ho? Well done, well done. You might want to, I don't know, put this somewhere you can see it in the morning when you get up from bed on the ceiling or something like that, or whatever, okay? Memorize it. By the way, for many people, like myself, I actually, to be honest, I don't usually use this. I just remember it's bottom times the root of the top minus the top times the root of the bottom, all over the bottom square. If you like better, if you're not a fan of the high and the low, you could do high and low, and then it's low D high minus high D low over low low, right? So, all right, whatever. But one way or another, this is something you need to know, right? So, one way you'll get to know it very easily, I think, too, is by practicing it. We'll be using it all year, all the time. So, eventually, you'll commit it to memory. Let's again note that this is not just. It's very tempting when you first encounter the objects of calculus to like just be like, oh, the derivative of the quotient. That's just going to be the derivative and the derivative. Well, not quite. It's quite a bit more complicated, as you can see here. Here's a function that we've never been able to take the derivative of before, right now. So let's give it a try here. And to the extent possible, simplify the result. Was that life-changing? Okay. Don't tell me. You think it's funny, but you'll be doing this in your head right now. You'll be thinking, okay, yeah, how do you minus how do you over door? And you're welcome.
So I guess that's two x plus x squared plus 3.
You've got a song for this instead?
No, it's quadratic.
I know. I just meant maybe you could come up with a song.
Oh, I don't know about
The other thing you could do is forget it and then just rewrite it every time you need it too. We'll go through the proof of this in a second. You actually don't really like the proof of this. Okay, even though you've never done it before, I'll take a volunteer who wants to just tell me what, not the simplified version, but like you're in middle school. Yeah. This is serious. There's nothing funny about it.
Yes, it's really funny. Oh,
I think Rebecca wanted it, actually. Did you want to get it? All right, so, yeah, go for it. So, no, not simplified yet. We'll get to that. But just the first thing that everyone wrote down. Listen and make sure this is what you have. Max?
The quantity of x squared plus 3
Okay, bottom.
times the quantity of 6x squared plus 5
Times the derivative of the top.
minus
Hey, listen, guys.
minus the quantity of 2x to the third plus 5x times 2.
Okay.
And all of that over x squared plus 3.
There you go. Yeah? Is that what you wrote? And then simplify the result. I don't really actually care to do that right now that much, but I trust that you will simplify this numerator. Notice there are lots of things that you can collect like terms on, so knock yourself out. Arguably, multiplying out the denominator is not like the great use of our time. I don't know if that's simpler or not. You can though, okay? It's certainly true that it's not like we'll have, up here it might be fruitful because we can actually combine like terms, but down the denominator, expanding it maybe makes it more complicated. I don't know. Simplify is a little bit of a nebulous instruction, isn't it? So, okay. All right, for the proof of the quotient rule, I want to set you in the right direction, and then I want to give you just a few minutes to see if you can come up with the proof, okay? So, let's consider a function h, which is equal to two other functions, f and g, divided by g, excuse me. Here's my tip. This is the one hint I'm going to give you, and then I'm just going to let you like roll with it, see if you can get it here. I want you to multiply both sides of this equation right here, h equals f over g, by g, and then take derivatives on both sides of that equation and just see what happens. In the end, remember our goal. What's our goal? Is eventually to find. Eventually, we want to know what is the derivative of h, right? We want to know what is h prime in terms of f and g and f prime and g prime, right? So that's the end goal. Give it a try here. I want to see how you do.
What if I have like f of x? Can I like x
I'll give you like a total of 5 minutes of productive struggle. See if you can do it. Work with people at your table.
derivative of both sides. I don't have both sides, but I don't know
Good. And now you know how to do the derivative. Generally, like, it's not telling me there's too big of a difference right now. So you want us to be. There's no.
You've asked me that like 3 times. Still now.
Like, when studies say like X. I feel like for the work, they don't specify.
Maybe not.
Figure it out. If you solve for h prime, good, but make sure there's no h anywhere. I want h prime in terms of f and g and f prime and g prime, right? So I need, like in the end, I want h prime equals something, right? In terms of f and g and f prime and g prime. See if you can get me there.
I don't have enough space, so I'm going to try to make it happen. Nope. Thank you for that for hours.
Yeah. Can you prove it? Yeah.
I don't think it's possible. It's like overpowered. Except they're like 10 times right? That would use this for artistic value.
My heart be still. All right, we have one person who got it. Good job.
Wait, who? Amy?
I can't tell you. She would like to keep her identity secret. It's okay. I didn't want to be known as like
I see what we're this is G prime. That was our first mistake. Oh, okay. We didn't have you live with basic
you know about that.
mathematical error.
I mean, H.
You get to say that.
Oh, yeah, that's right. I like that.
If you try, use like limits, what you've done.
You already know the answer, right? You know, you should get what it said on the last slide. You know, g f prime minus f g prime all over g squared, right? You guys
You're doing math now.
Is that you getting it?
I don't have it at this point.
I thought it was fine, and I got very
What? Real good. She's not Also, you told me this exact. You really went this exact. That's really awesome. Yeah, I
Did you have another challenge for me? What? Did you do that one? Those are correct.
figure out how to make.
All right. Let's see at least how far you got. Did you get here? Did you get here? Yeah. Good job, everybody. Good job. And then I did tell you to take derivatives. So hopefully you got here. Yeah? Haven't lost anyone yet. And then I told you the thing the thing we're looking for is h prime. So I moved everything over the one side and I divided by g. So you get that? Yeah? So far so good? And then, Amy, you want to tell us like what the move is now? Because it seems like we're stuck. Oh, h. Let's not forget. H is also known as f divided by g, isn't it? So make that substitution, and then you've got it. Right there it is. That's the quotient rule. If you'd like to make it look like the previous slide, you can multiply by g over g. But I mean, right here we have it, don't we? Yeah. G squared. Thank you. Does that make sense? Like changing, right? Like changing. Okay. No one will have to ask you to prove it. I just thought just for the love of the game, don't you want to know why it's true? All right, let's do 2 more of these. This is my last slide as the announcements are going.
And for the girls, we have Vanessa Bonton, Kalia Wallace, Donna Sertan, Sophia Balwan, Gabby Phillips, Kelly Phillips, Anna Barber, Ryan Clark, and Aaron. Congratulations to you all. Thanks so much. Everybody have a great day.
It was something.
All right, so you guys almost done with the quotient rule on this one? So bottom times the derivative of the top. Or, again, if you don't have to use the quotient rule, maybe you don't, right? Before we do any calculus, you might like to do a little bit of pre-calculus, yeah? What is this? 1 minus 3x to the negative second minus 4x to the negative 4th plus 2x to the negative 5th. And I think maybe taking the derivative of that, it doesn't say how to do it. Without the quotient rule, though, might actually be an easier thing to do, right? Okay. And then it looks like the bell's about to ring in a second, but just stare at this question down below and make sure, so we'll have to finish this one here. And just make sure that you do, in fact, have all the information to answer that question. Very, very, like, AP likes to ask that kind of question, right? So I apologize to cut us short on time. We can pick up there tomorrow a little bit. And I love you all. Okay. Yes, Matthew.